what I'm going to try to do here is tell you a little bit about quantum measurement. And one of the things I really enjoy is the fact that this is supposed to be a young physicists meeting. That means hope pictures of Einstein, and I could show you pictures of the two of them talking to each other and talking and talking and talking. And then I could show you, okay, then comes the next generation, you know, and, you know, you've seen these names. Hugh Everett is actually quite important for what I'm going to be talking about. But again, you do not have to know any of this stuff. There's obviously a new generation now talking about quantum measurement, and then there's Wheeler. There's always Wheeler, you know, who has thought very deeply about it. But I'm not going to do any of this. What I want to do basically is make you forget everything you've ever heard about quantum measurement and start from scratch. And indeed, everything that I'm going to be talking to you from now on, you don't have to have heard anything about the quantum measurement problem. I'm going to basically introduce everything from the very beginning. Let me actually try to get rid of this thing up here. Well, actually, I can just move it down here. All right, here. All right. So, okay, let's actually start with classical measurement. So what is a measurement? So from my point of view, the way I'm going to treat classical measurements, I have a system that can be in a number of states. In this case, you know, it's discrete states. Now we could say, well, you know, real systems don't have discrete states, but to some extent, measurement devices do have discrete states. And so it's just as well that we're going to assume that the system also only has discrete states. Then we have our device, and it is actually in a prepared state before we have the two interact with each other. Whereas we don't know, of course, in what state the system is. That's what we want to know. Now let them interact with each other. And after the interaction, which is of course not a random interaction, it's a very specific interaction that you have to do when you're doing measurement. You want to have the device reflect the system, right? Which I here showed you that, you know, the needle points in the same direction. That's really it. That's a classical measurement. You know, you extract information about the system. In a sense, it's a copying operation in a way, right? You're copying the state of the system onto the state of the device. All right. Or here, by the way, if you do it information theoretically, you would say that, you know, the system has an entropy. You know, this has n states, so the entropy is logarithm n, and the device has also n states. You know, in fact, these are the n states that you can resolve. Of course, the system could have more states. And then after you make them interact, essentially, you have this Venn diagram where you have this shared entropy, which is in fact the information that you extract. And as I said, the system might have more states that you do not resolve, in which case this Venn diagram has this little piece on the left. Now, but it's important that your measurement device actually has no entropy given the system. That means that the device essentially is noiseless and is fully determined once the system is given. That's what this information theory diagram is supposed to tell you. Now let's move to quantum physics. So I'm going to do things here very simply with position measurements. Obviously, you know, later I'm going to be looking at qubits, but, you know, for the introductions, let's just do position measurement. So our quantum system is in state X, and our measurement device is in state 0, just like we did for the classical measurement. Now, what we want to achieve in a quantum measurement is we want to make them interact so that at the end, the measurement device reflects the quantum state, right? So how do we do that? And the answer is there's actually a very nice unitary operator that does that. It's e to the I position operator times momentum operator, where that obviously is the Hilbert product. Let me show you how that works. So I add, you know, I work on this product state of the quantum state and the measurement state with this unitary operator. And you see that the X operator basically applies to the X state. It puts this eigenvalue there. And now in the next phase, basically, I'm going to be moving the this state using this operator. And as you, of course, remember from Quantum Mechanics 101, it moves it exactly by X. So indeed, now what I've achieved with this operator is I went from the product state where the measurement device was just in its initial state to one where I'm copying this quantum state into this measurement state. Now, great. What's the problem? Well, here comes the problem. Suppose Q is in a superposition of two position states. Well, I only have one measurement operator, so I'm going to apply that too. So obviously, I'm going to get, well, first of all, I'm going to write this, as the sum. That's the linearity of quantum mechanics used right there. And then I'm going to use this operator on each of these states. And of course, here I'm pushing it to X, and here I'm pushing it to Y. So the trouble now is that what I wanted in a measurement, I wanted to actually have a copy of the quantum state in the measurement device, and that didn't happen. In fact, I have this entangled state. So why did it not work? And the answer is, well, a perfect quantum measurement is a cloning operation where you're trying to clone the quantum state into the measurement state. But cloning is impossible. In fact, that is the no cloning theorem of quantum mechanics. So what that means is in quantum mechanics, perfect measurements like I would like to have them like I have them in classical physics, they are simply impossible. The best you can do is approximate measurement, which is essentially, with approximate quantum cloning machines. And I should say perfect measurements of unknown states is impossible. If you have a prepared state, you can actually copy that just fine. There are, cloning machines only don't work on unknown states. And what that means, in fact, if you don't know what that means, I'm going to talk about what unknown states even means in about 10 minutes or so. All right, now actually, let's just do the formulation of projective von Neumann measurements. And I call them von Neumann measurements because to some extent, it's different from what you've heard about with Bohr and stuff like that. I'm not going to talk about wave functions collapsing. In fact, I'm going to try to do everything on the level of the wave function. After all, we know how to deal with wave functions. We have a Schrödinger equation, and all dynamics is unitary. I'm not going to introduce some sort of Deus ex machina now something has collapsed. So let me show you how it works. First of all, I'm going to say the quantum state is a superposition with amplitudes alpha, and in this case, I have d different states, so it's a Q-dit. Okay. Here are the complex amplitudes, and in the following, I have a sort of color scheme where the quantum state itself is always going to be in this pinkish color, and then I'm going to have measurement devices and so on. They all have different colors, so that we can sort of easily keep them apart. So I'm going to actually now introduce the first measurement device, A1. It's called an ancilla, and I'm going to have it in yellow. It's called ancilla because, in fact, that's an ancient Latin term for helper. So these are our helper states that allow us to do the measurements. So we're going to do it just like we did it for the position state measurements. So we have this unitary operator. Instead of e to the I xp, it's actually now written in terms of a projector on the state x1 and an operator that is going to be moving the needle. Okay, so the projector, you know how it looks like. And this operator, basically, if I'm acting on the zero state, it moves, the zero state into the x1. So you can think of it as a ladder operator. In fact, it kind of really is one. All right, so when I apply this, obviously, what happens is that I'm pushing all of these states here, and basically, now after application of this unitary operator, I have an entangled state. Remember, this is the quantum state, and this is the measurement device. And you see, yes, they reflect each other, but of course, it's an entangled state rather than a product state. So in this case, the measurement operation is an entanglement. And by the way, von Neumann has written all of this down already. So this is not new from me or anybody else. Okay, all right. So let me just show you that with this von Neumann measurement, all the standard results that you are otherwise familiar with, if in fact you have ever looked at quantum measurements, you will find those two. So here's our quantum entangled state. I can now trace over the measurement device so that I have the density matrix of the quantum state itself. There it is, which I can also write in terms of these state projectors P. And now the standard way in which you are taught how to get the probability that my measurement device shows any of the particular eigenstates, it's this one. You take the density matrix of the quantum state, you take the projector into that state and you trace over the quantum state. That gives you the probability that I observe x1. And in fact, in this case, it's just the square of the amplitude. So I just showed you that, you get Born's rule. Of course, you get Born's rule. If I couldn't get Born's rule, then none of this would get published. All right, great. Nothing new, therefore. I can also, of course, trace over the quantum state for this joint wave function, and I will get this density matrix of the measurement device, where on the diagonal I have all of the probabilities to observe any of the eigenstates x1. So far, so good. Now we can ask the following question. Well, look, Chris, your ancilla is a qubit. Why would you call that a measurement? It's just an interaction between two quantum qubits, right? The answer is, well, that's a good point. To see that it's really a measurement, I actually have to show that this ancilla, this qubit, can be amplified incoherently. And what does that mean? Is the amplification means essentially that the information in that one qubit can be copied from this one qubit to many, 10 to the 23, if you want to. If you can do that, then this is really a measurement where the measurement device is classical, even though I've written everything in terms of qubits. Now, you need to understand, of course, that classical physics doesn't exist. So everything is qubits. It's just sometimes you have 10 to the 23 qubits in one big measurement device, and sometimes you're only measuring one. But in the end, what looks like a classical instrument is when the information in this one qubit can be copied into many. We'll do that operation in a moment. So basically here, that's what I mean, right? If this can be done without changing any of the entanglement properties of the system, then that's what we call a quantum measurement. There are cases where this cannot be done, and I will talk about these cases. These are very important cases. All right. So incoherent amplification means loss of any qubit does not change the entanglement. So in other words, if this happens, your measurement device doesn't suddenly change. Everything still looks the same. So we will say that a qubit is amplifiable if it is diagonal in the measurement basis. I'll show you in a moment what I mean by that measurement basis, but that's a theorem that is proved in the paper that you see listed down there. So I'm not going to go through that proof, obviously. So when we look at the density matrix of the measurement device, we see that, oh yeah, it's diagonal. And in fact, these are the eigenstates they're in a sense, they're of course, in the same basis as the quantum system, but they are really the eigenstates of the measurement device, and it's diagonal in the measurement basis. So in a sense, this particular measurement, yes, I could amplify this qubit. The fact that it was written as a qubit didn't matter. In fact, here I'll show it to you. Here have your quantum state. You see that it's actually entangled with something that's called the reference state. We'll talk about this in a moment. But then, we're going to entangle it. What we're going to try to do is measure this qubit, right, with some classical devices, right? This is how we're going to do the amplification. If we do that, it's actually easy to do. I'm not even going to go through it. We can do that with n1s. What you see here is the density matrix of all these measurement devices that just measured that qubit, and it's also diagonal. So in other words, this is a measurement of a quantum system using a classical device, even though I wrote everything in terms of qubit. Everything looks just normal. So yeah, if D is diagonal, it is amplifiable. This diagonal density matrix just means that all the observers, in a sense, every element of your measurement device agrees with every other. It's a consistent measurement device. All observers agree. There are no off-diagonal elements in this matrix, and that means, of course, that the wave function looks like it has collapsed. Like, if you get one state, x1, that means, you would assume that the quantum state is, in fact, in x1. Okay, that's what no off-diagonal elements means. All right, now that we've done that, let's study the measurement of an arbitrary quantum state. So what does arbitrary mean? It means it wasn't previously prepared. That means you don't know what basis to measure it in so that there is no noise. Because as you know, if you measure a quantum system in the basis in which it was prepared, then you will actually, get the same result over and over again. So that's what arbitrary means. Now, any state, any quantum state that is not a maximum entropy state is actually partially known. And a maximum entropy state is one where each of the states, in a sense, are equally likely. Okay. So, for example, what a completely unknown quantum state looks like is this, where all the amplitudes are 1 over square root of d, or in the density matrix have amplitude 1 over d, where d is the number of states. Okay. Because if it was not, then in fact, you would know something. That's what, knowledge means. Knowledge is departure from maximum entropy. So unknown quantum state, by definition, means that it has to have maximum entropy, in this case, log d. Now, let's introduce the purification of this quantum state. There's a theorem that is easily proven that every density matrix like that can be written in terms of a wave function, where this R is called the purification. Okay. Now, what these purifying states are, we don't really know. They're not accessible to us. It's stuff that your quantum state is entangled with if it is a mixed state. As far as I'm concerned, really what this represents is all of the quantum states that your quantum state has previously interacted with in its history. We know it's there. We cannot write it down except like this. And in fact, that's all we need to know about it, because we will never make any measurements on that state. It's not accessible. However, mathematically, we are allowed to write it down. That's a theorem. So there's a correspondence between those. All right, now we have written the quantum state like this. Of course, again, in pink is the quantum state, and the reference we will always show in blue to distinguish it from the states of the measurement device. So that's the trick that we're using, so that we can always do all of the math with respect to wave functions rather than density matrices. It's this purification. All right, here it is, our state. Now we're going to be measuring it using a detector A1. To do this, I'm going to have to write the quantum system in terms of A1 spaces. Okay. Now you might say, how am I going to do that? Because I really don't know what the basis of X is. But you will actually see that it doesn't matter. So watch this. So first of all, yes, we can write X is 0, these states, in terms of states X1, which are in fact the eigenstates of the measurement device. And then I'm going to apply my operator. Here, this operator will be applied to that. Here's the ancilla, here's the quantum state, and here is the reference. So what this measurement device is going to be doing, it's going to be copying this state over into there. Okay, so once we do that, we see, okay, we have this system here. But we still have this weird rotation matrix, which in a sense we don't know. Where I rotated the quantum state into the eigenbasis of the measurement device. Turns out that we don't actually need it, because I can actually write the reference in terms of the A1 basis also, and it turns out that that's rotating it, in the other direction. I'm not showing you the proof. Now you just have to believe me. So once I do that, I actually can write the joint state of the quantum system, the reference system, and the ancilla as an entangled state of 3, and there's no more rotation matrix. Now everything is written in terms of the eigenbasis of my measurement device, right? Because X0 is the basis of the quantum system, X1 is the basis of the measurement device, and the reference, of course, has to take on the same basis as the quantum system. This is also known as the GHZ state, by the way. Great. Now that we have done this, and this is, of course, the color scheme here that you remember, quantum system, reference, measurement device. Let's do the following. Well, let's first take a look at what that looks like information theoretically. So if this Q was a qubit, then you can easily calculate that, in fact, I have a shared bit between the density matrix of the quantum state and the density matrix of the measurement device. In other words, I have a perfect measurement as far as classical extraction of information is concerned. If I have a qubit, of course, this information is log d. So everything looks good. And I remind you, A1 could be macroscopic. And here I've just written it, the wave function, with a macroscopic measurement device, where I have 10 to the 23 states here that all point into the exact same state. Now, let's actually do 2 consecutive measurements. That's something that happens a lot, where you basically measure a quantum state that you previously measured in a different at a different angle. And when you're doing quantum optics, you would be doing that using polarizers. And so essentially here you would have the second polarizer at an angle to the first polarizer, which did your first measurements. Now, the angle is essentially the angle between the eigenbases of the 2 measurement devices, and it's a unitary matrix defined like this. If you do qubits, you've seen it before. It's just a rotation, because we're gonna forget about complex phases here. All right, now that I have this, I can easily write down what is the result of a second measurement on top of the first one. It's written here. I have actually the derivation of how that is done. Let's actually go through that. I'm going to use green for the second measurement. So here is the measurement after the state after the first measurement, if you remember. Now I'm applying my second measurement on it, and it acts on the quantum state and the second ancilla only, and nothing acts on the reference, nothing acts on the first measurement device. The first measurement device won't be touched anymore. So let's act on that. Well, the way this is going to be done is that this operator is going to be copying this state into there. To do that, I have to write Q in terms of the second measurement basis, which is done by that matrix that you've seen before. And there it is. That's the result. You have a wave function now consisting of the quantum state, the reference, the first measurement and the second measurement, and a rotation matrix between the first and second measurement basis. Great. Now what? Well, let's first check that everything is still exactly the way it should be. So here's the density matrix of the 2 measurement devices. Turns out they're both diagonal. So in other words, they're both amplifiable. So this is exactly what you expect. You have one measurement by one device that keeps your classical value of the measurement, and a second one, the amplifiable. The fact that I've written everything in terms just qubit doesn't make any difference. Here are the standard textbook results. If I trace over everything, here are just the density matrix where on the diagonal are the probabilities to observe each of these results. And because I started with some completely unknown states, they're all 1 over D. And here's the density matrix for the second measurement device with probabilities Q2, which are written like this, which is, involves, of course, these rotation matrices. And you can see that this is just the probability to observe outcome x2, given that my first measurement had actually observed x1 times the probability that I observed x1, which here is, of course, just 1 over D. That's the standard quantum physics result. In other words, every known result about 2 consecutive measurements works exactly like it should with this formalism. That's why I'm saying, while this formalism isn't exactly how everybody else teaches it, you shouldn't be thinking about the old ways of doing things. This is the way to do things, and you will not make a mistake. All results that will exactly come out. And again, of course, it looks as if the quantum state collapsed into the eigenstate of the second observable, right? All right, but now we've done 2 measurements. Let's do one more. I mean, what could possibly go wrong? Well, famous last words. Watch what happens. So we start, well, we're going to do a third measurement, which means we just have a third polarizer, okay? Seeing this in terms of quantum optics is nice, because what you don't want is that your measurement is completely destructive, because then I can't really measure the quantum state anymore. So we introduce the rotation matrix between the third and the second measurement device. And then, you could have written down already what is the wave function after the third measurement, because what happened is, of course, that the x3 is being copied over here, okay? So you first write the quantum state in terms of the basis of the third measurement, and then you're using this copy operation to copy it. There it is. This is the quantum state. Again, quantum state, reference, first measurement, second measurement, third measurement. It's now in purple. Fine. let's take a look at a few things. Here is the density matrix of the 3 measurement devices. Easy for you to calculate. Here is, in fact, the density matrix of the first matrix. You see, in fact, that this density matrix is a product of 3 density matrices. Here's the A1 matrix of the first measurement. Here is, in fact, the measurement of the density matrix for the third measurement. And you see it is diagonal. This one's diagonal. And here's the one for the middle one. And here is a surprise. That thing is non-diagonal. Now, you can ask yourself, how is that possible? Because you just performed the third measurement. And before you did it, the second measurement density matrix was diagonal. And somehow the third measurement messed with the second measurement density matrix. How is that possible? I'm going to show you how that's possible. It seems crazy, but it's not. So what happens here is that apparently the third measurement revives the coherence of A2. You know, when I said that A2 was incoherent, well, it was incoherent in the sense that you could amplify it. Now you can't amplify the second measurement device anymore without destroying its entanglement with everything else. You can amplify the first, you can amplify the last, you cannot amplify the second. So what went on here? All right, let's take a look at it first. So here it is. This is a density matrix of the 3 measurement devices. And you might wonder, Chris, why aren't you showing us a density matrix of the quantum state? And the answer is, nobody cares about the quantum state. The stuff you're looking at is measurement devices. You don't look at the quantum state. So we're tracing out the quantum state. You know, we're only looking at the relative state between these 3 measurement devices, because after all, that's what's accessible to us. So how is that, you know, different from the standard picture of quantum measurement? And the answer is, well, if you had assumed that measurements collapsed the wave function, that there was no way that you can actually move from a diagonal middle matrix to a non-diagonal middle matrix. In fact, the collapse expression, if you apply Bohr, would look like this. So in other words, this theory of quantum measurement that I'm showing to you gives results that are different from what Bohr would tell us. Wow. Okay, well, let's digest this a little bit. First of all, wouldn't we see this? Well, the answer is not necessarily. Here's, by the way, I'm showing you the difference. The difference here is if you put a delta x2 prime and sum over x2 prime, then you would, of course, get that. But that's because this is a non-diagonal matrix and this one is a diagonal one. So this difference is actually not visible in pairwise correlation between detectors. I'll show you that now. Pairwise correlation is like correlation between A1 and A2, A1 and A3, and A2 and A3. So if I trace over A2, I get the density matrix of A1 and A3, and they're both diagonal, which is what collapse picture would have given us. If I trace over A1, then I get this density matrix, which is also diagonal, and is what the collapse picture would have given us. And if I use the identity over here, then I can trace over A3, and I get the density matrix of A1 and A2, and also it's diagonal. So in other words, you do not see this reoccurrence of coherence if you only look at pairwise. And most of the time, people never look at more than pairs of measurements. All right, now let's do an example so that we can actually check this. We're going to do the qubit example. And we're going to put very specific angles, namely, we're going to put the angles in such a way that you're going to be measuring a state so that you get a maximum entropy. In other words, you know, I get up and down measurements, you know, half the case. Okay, so that's what you see here. These square elements of these matrices are all 1/2. And then my approach to measurement gives this density matrix for this triplet of the density matrix of the 3 measurement devices, whereas the picture that and by the way, this is sort of the interesting quantum information theory Venn diagram between those 3 measurement devices. If you trace over any one of them, this just looks like the standard 0, 1, 0, but in fact they're highly entangled. Even though if you only look at pairs, you look like that they're independent, but they are not. Underlying is a quantum wave function that entangles these three measurement devices. The collapse picture basically says in this case that these three measurement devices should be completely independent, and the quantum Venn diagram would look like that. Now, I gave a talk about this in a quantum optics lab in Canada, and one of the students there seen this, and he decided to test this. In fact, in his thesis, he wrote, "This is a rather bold claim. The projection done by the measurement does not on its own collapse the state. This, of course, requires verification. The most obvious way to do this is to measure or reconstruct this density matrix of these three measurement devices that is encoded by different possible paths a photon may take, and show that it has coherences where one would not expect to see if the state was collapsing between each measurement." So that's his thesis. We're going to see some results from his thesis now. So this was done in the quantum photonics lab of Jeff Lundin at the University of Ottawa. So the way he does this measurement is the following. He starts out with a mixed quantum state. And by the way, I'm just showing you here the case with a mixed quantum state. In fact, he can start out with a pure quantum state or a mixed state or anything in between, and sends this into a polarizing beam splitter, okay, which does this measurement for you. So you get a transmitted beam and a reflected beam. Now you put sort of phase rotators on each of these beams, the same one, which basically change the angle of your measurement device. And then you actually put two polarizing beam splitters in these paths. You have to do it in a coherent manner, and that's of course the hard part. But I'll show you that they're able to do that. You can't do that on an optics table where these are actually two different ones, because they will not be coherent. So here's your second measurement, and after that, of course, you are changing the axis again for your second rotation, and then you're doing it again. That means you have 8 different outcomes. But again, yes, you have to do all of these, like these last steps, they all have to be done in a coherent manner. If we do this with this rotation angle pi/4 that you saw, then the density matrix in the Bohr picture, like I showed you before, is a completely random matrix. Like, because of course, if you measure at pi/4, you get a 50-50 random result. That's the Copenhagen density matrix. But if you're applying this unitary von Neumann approach to measurement, you realize that the density matrix is actually not diagonal and has these 8 off-diagonal pairs, which tell you that there is strong coherence in between some of these different beams here. So how do you measure that? So they can actually do this experiment. And so in order to make this coherent, what you do is, you actually go by small angles. Here's just 2.7 millimeter in the X direction for the first measurement, 2.7 millimeter in the Y direction in the second measurement. And then you're splitting these again by 4 millimeters so that you can distinguish it from the 2.7 millimeters. And, these people have been showing for years that you can do that in a coherent manner. Here you see the 8 beams that are going to come out. Now I'm saying beams, but of course we're going to do that in the low field regime, where essentially there's only a single photon ever traveling, in between the source and the screen. So here's the typical type of picture that you might see. Of course, this picture has been taken in the strong field regime so that you can see them, but they are going to be recording clicks. Now, what you can do is you can check the coherence between any pair of these beams. And if my picture is correct, then in fact, you should be seeing, for example, coherence between this pair, this pair, this pair, and this pair. That's these off-diagonal elements. They basically tell you that there should be some coherence. So the way they measure this coherence is that they have a way to actually bring these things back together again to measure interference. And I'm not going to go into that technology in particular, because I'm really not an expert in it. But that seems to really work. What this does is it allows them to reconstruct the underlying wave function actually. So it's called a 4F system that allows you to reconstruct this density matrix. And again, we're going to check it in the weak field single photon regime. So this is, in fact, this coherence matrix that Davor Kuric has measured, and you see immediately, this is high coherence, this is low coherence. Of course, there should be zeros over here, so in this part of the density matrix. So this is all zero coherence, but there's strong coherence in these off-diagonal terms. All right, great. Now let's actually do a little bit of quantitative measurements. So what we're going to do is we're going to be calculating the purity of the density matrix of the 3 measurement devices as a function of the purity of the preparation of the initial state going into this device. The purity is, of course, just the trace of the square of the density matrix. And of course, we're going to keep here this second measurement ancilla coherent, right? So if you remember, you basically get the beam split 3 times. And the advantage of making this in a quantum optics experiment is that we can actually protect the coherence of the intermediate ancilla because it's in a beam, right? So this beam is not going to now interact with a bunch of other qubits. However, we can also mess with the coherent of the middle state by actually letting the time degree of freedom of this middle photon, in a sense, decohere. So in other words, we can do this experiment where we are keeping the second measurement ancilla coherent and then repeat it where we actually are letting the second measurement ancilla decohere. And if you remember, if I let the second measurement ancilla decohere, I should actually recover the collapse picture. But the fact is that if I can keep it coherent, I should be able to show that that the result is quite different. So here's what, first of all, I'm giving you the theoretical result for the purity of the quantum, of the detector system as a function of the purity of the initial state. And basically here at 0 theta, that is actually a pure initial state. And here at a quarter, that's actually the mixed initial state. Theory gives 2 very different predictions for the no collapse picture, the one I've been advocating, where you have these coherences in the density matrix. And the collapse picture actually predicts this for the purity of the density matrix. Now, let me show you what the measurement results are, and actually analyze Davor's data myself in order to do this plot. This is what you get. It's not perfect because there seems to be some bias for a pure initial state, but that basically rules out a measurement process model where measurements actually collapse the wave functions. Now, if we do the measurement, but we are allowing the second ancilla to decohere, we have that data also that actually perfectly reproduces what we should be expecting. So, wow. So what now? Well, okay, I'll come to a few conclusions about this. So first of all, I'll just summarize what I said. I said that, a relative state approach to quantum measurement suggests that, in fact, wave functions never collapse. I never talked about a measurement collapsing. If they had been collapsing, then, we wouldn't have gotten the result that we got. But I've also shown you that in most cases, I will not see a difference between a collapse picture and a no collapse picture. The approach makes predictions that actually differ from Bohr type collapse pictures when 3 or more measurements are performed in the same quantum system. If I only do 2, I will not see this. Remember, because of this pairwise rule. And in fact, like I showed you, the experiments favor this no collapse by over 10 sigma. So basically, the Bohr picture is very solidly ruled out by these experiments. So what does this all mean? Now comes a few sort of philosophical takes on what that means from quantum physics and quantum measurement. And obviously, I could have started with philosophy, but I didn't want to. I wanted to see how to do quantum measurements mathematically and how that actually looks like if I measure this. So the first thing is that the result implies that the state of the measurement device does not, in general, reflect the state of the quantum system. Now, in a sense, this looks crazy at first. It's like, well, but in a quantum measurement, I want my measurement device to reflect the quantum state. But the answer is you can't have that because that's quantum cloning. The quantum state is in a superposition. Your measurement device cannot be because it's classical. So it will not tell you what the state of the quantum system is. However, it will tell you something else. It will tell you what the state of other measurement devices are. So this is what this whole idea about relative state description, which is essentially Everett's description of quantum measurement, is. The only thing in a sense that you can ascertain is relative states between different measurement devices. That's what you can have. But you can't actually make statements about the state of the quantum state itself. Now, we can actually infer the wave function by indirect methods like the quantum state reconstruction that I just showed you. But your standard clicks on a measurement on a device, they are not telling you something about the quantum state. So I mean very much then if you see a photon coming off of a photomultiplier tube or like let's say a CCD, and this pixel lights up, it doesn't mean a particle hit at that point. It really didn't. For a very simple reason. Particles don't exist, only waves exist. So a click by itself means nothing. The measurement device lies to you and it has no choice. You're asking it something it cannot answer. It has to respond to something. It can't just be quiet. So it's going to click and it's going to say spin up. But does it mean spin up? It doesn't mean it at all. So you just have to move away from this thinking that your measurement device says something about the quantum state. The only accessible reality, therefore, is relative states between different measurement devices. Indeed, once you start thinking about it deeply, you realize it's not a problem because theory actually predicts these relative states. In fact, for most of what we want when we compare experiment to theory, we are not interested in a sense what the quantum state is. We are interested in what relative states of detectors are. Let's say at one point and then another point and another point. Preparation, state evolution, and so on. In other words, the theory in any case really works by making predictions about relative states of measurement devices. So in other words, the fact that you don't know what the underlying quantum state is irrelevant. You just have to forget about this idea that your measurement devices are a direct reflection of the quantum state. It cannot be. Indeed, the longer you think about it, you realize we don't need to know the underlying wave function to calculate these relative states. And the other thing I wanted to say is that some people say, oh, isn't this a many worlds picture of quantum measurement? And some people have been pushing this interpretation, and I always sort of recoil from that because none of that makes any sense. The many worlds interpretations are flawed in so many different ways. I'm not going to go into that. It's not a many worlds picture of quantum measurement. There's only one world, but we find that the amplitudes of unrealized quantum states are still present. And when I say unrealized, it just means what my detector didn't tell me. Like if my detector says up, I'm telling you, it doesn't mean the quantum state is up. It has an up amplitude and a down amplitude. And I'm calling the down amplitude the unrealized one. But it's still there. It's just not being shown by the measurement device because the measurement device can't show it. We don't normally notice that there are these unrealized quantum states that are still there, but they can actually be revealed by judicious experiments. Clearly, the one I just showed you did that. It showed you, when I was telling you that the coherence was resurrected, it's because these amplitudes were there all the time. You can find them if you look hard enough. Quantum eraser experiments are another way by which you can see that you can sort of see that the amplitudes that you thought had all died out were all collapsed. They are still there. And that's actually all I wanted to say. And I wanted to just thank all the people that helped me in this research. Most of all, Jennifer Glick, who was my grad student in the physics department here, who is now working on quantum computation at IBM, and the people from Jeff Lundin's quantum photonics group that worked on this experiment, Davor and Lambert. And with that, I'm happy to entertain questions.